Welcome back. So, in the last class of this course on blockchain and its application, we are talking about this open consensus mechanism, and we have seen the broad idea, the broad environment that we are going to consider. So, we are going to consider an asynchronous open environment where we want to design a consensus mechanism while satisfying the FLP impossibility. So, we cannot violate FLP impossibility. So, safety and liveness cannot be satisfied together. So, today we are going to see that in case of the Nakamoto consensus or the proof of work mechanism, how we can give priority to liveness over safety, and accordingly we can design an effective consensus mechanism for an open network. So, the topics that we are going to cover today are as follows. So, we are going to talk about this Nakamoto consensus or proof of work in details, and in that context we are going to talk about the idea of block mining in a Bitcoin blockchain, or rather in a proof of work blockchain. So, these are the keywords for today: proof of work or POW, the block mining, and safety liveness. Well, so, this safety versus liveness or safety and liveness, these two properties we need to always keep it in mind while we are talking about any kind of consensus mechanism. So, these are the point where we stopped in the last lecture, that I have an existing blockchain and I have a set of miners. Now, these miners are the kind of special node who participate in this consensus mechanism, and they try to mine a new block. Why we call it as a mine, that terminology would be clear to you later on, maybe in the next lecture, not even today. But for the time being, just assume that the persons or the participants who are participating in this procedure of consensus, that means generating a new block from the transactions which are coming from different clients. So, those participants we call them as the miner. Well, now in a typical Bitcoin network, anyone can join as a miner. So, any participant, say if you have an Bitcoin account, Bitcoin wallet, and you are a part of the Bitcoin network, you can participate as a miner. So, anyone can participate as a miner. So, there are such nodes that who are participating as the miners, that means they are adding the new blocks in the blockchain, and the first task of the miner is to hear the ongoing transactions that have been floated in the Bitcoin network. Well, now the transactions which have been floated in the Bitcoin network, they keep on collecting those transactions, and after collecting those transactions, what they do, that they put it on their list of unconfirmed transactions. So, that we call as the unconfirmed transaction list. And the important point that I have mentioned in the last lecture, that because we are talking about open network and rather an asynchronous network, it is not necessary or it is not required that every miner has heard of all the transactions that are going on. It might happen that some miner has received some set of transactions, another miner has received another set of transactions. There may be some good amount of overlapping, but it is not necessary that there need to be kind of exact overlapping between the transactions that they have heard of. Now, once they have this set of transactions, so the next question, immediate question comes, that from this set of transactions, how we generate the next block. Well, so this entire procedure in the open consensus mechanism in an asynchronous environment, I need to ensure that the behavior from individual miners are what we call as the asynchronous. So, this asynchronous behavior is a little bit, the idea is a little bit different from what we call as the asynchronous channel. So, the asynchronous behavior means my behavior is not dependent to anyone else. So, I am not going to see what are the other miners or who are the other miners, what they are doing and so on. So, whatever I want to do, I will do it. Well, and the network will see that whether I have done the correct thing or not. So, if you remember that earlier we had discussed that when we talked about this brief history about this journey of blockchain, we mentioned that the broad idea that this open consensus mechanism they incorporated is an idea of challenge response. Well, so we are going to look into that challenge response in details in today's lecture. So, what happens here, that these miners they would like to create their new block. Well, and here I need to again think of, as I mentioned earlier, that the safety and liveness. Well, so you might getting bored with these two terminology, but whenever you are thinking about designing a consensus mechanism for a blockchain, these are the two things that you need to always keep in mind. Well, so every moment you need to ask this question, that whether I am being able to guarantee safety, whether I am being able to guarantee liveness, or which one I should give priority, whether I should give priority to safety or I should give priority to liveness. Because this FLP impossibility theorem, it has already stated that in an asynchronous network, even with a single crash fault, you will not be able to support consensus. And you remember that the type of faults that we discussed in the last lecture, that means the crash fault, the network fault and the Byzantine fault. Out of these three faults, crash fault are the kind of most simplest form of fault, where the nodes simply stop responding. Well, now even with a single crash fault, you know that you are not being able to achieve consensus. So, you need to give priority to either safety or liveness, and that way this idea of safety and liveness need to be crystal clear in your mind. So, this safety property here, for the ease of explanation, I have divided it into two parts. Well, so what safety basically tells in broader sense, that every correct participants will agree on a correct block. Well, so it has two different components. So, the first component is that the correct block, they should agree on a correct block, and the second component is that every participant should agree on a single correct block. That means, even if there are two blocks, both of them are correct, or you have two messages, both of them are correct, but it should not happen that 50% of the participants they agree on one block or one message, and 50% of the participants they agree on another block or another message. Well, that should not happen. So, everyone should collectively decide a single block. So, at a consensus, I should have a single output, not more than one output. So, this we actually call as the consensus finality. So, based on that, I have tried to divide this safety idea into two parts. The first one I call it as safety 1. So, what safety 1 says? Safety 1 says that the next block should be correct in practice. Well, what is mean by correctness of a block? The correctness of a block basically means the transactions which are there in the block, those transactions are the valid transactions. That means, the miner should do a validity check of all the transactions before incorporating them in a block. Well, so that they can ensure that based on the existing information that I have, and this existing information you have with the existing blockchain. So, based on that existing information that I have, this block or this set of transactions appears to be correct. If a transaction is a faulty transactions, then I simply discard that transactions, and I guess that in the previous lectures that Professor Shural has taken, you have already learnt about this Bitcoin script. So, Bitcoin script, in the context of Bitcoin, it is a way to check the validity of a transaction. So, you had these two different scripts, script seg and script pubkey, and by combining them two, you can actually check the validity of a transaction. So, the miners will do that validity check with the help of such kind of script, or depending on which particular mechanism is being utilized for doing the validation check, they will do that validation check. So, that way the block which is getting proposed, that is a correct block. Well, so the transactions are verified and the block contains the correct hash and the nonce. So, this is my first safety requirement, and in my proof of work consensus, this is something that we ensure. Well, so that means the block mined by a miner is a verified block, and the block that is getting proposed by a miner out of these 3 miners or 4 miners or the 100 different miners that I have, everyone would do that validation check and say that, well, this block is a valid block. So, I would add that block to my blockchain only after doing a check that this block is a valid block. So, this is the part of the safety that we ensure. Well, so I ensure that no invalid block will be added to the blockchain, that will be prevented. The second safety requirement, which is kind of more crucial, it says that all the miners should agree on a single block. This is something which is difficult to ensure. Well, what does it mean? That means that the next block that I am going to add here, that should be selected unanimously by the miners. Well, and this is challenging. Why this is challenging? Because whenever I am going to select the next block, if I want to ensure that the miners will select them unanimously, I need to have a way to make the miners talk to each other. Because otherwise you think of, you are in an open network, right? You do not know other miners. So, if you do not know other miners, you do not know what blocks the miners are going to propose. If you do not know that, how will you going to find out that that all the miners are collectively deciding on the same block? Because even the miners, they do not know each other. Well, so because the miners do not know each other, this is something we cannot ensure. So, my proof of work consensus mechanism compromises here. So, as I mentioned earlier that the FLP impossibility theorem says you cannot support both safety and liveness. So, what we do here, the first part of the safety which says that well, I am going to add only the correct, or I am going to consider only the correct things. By respecting that, the proof of work will ensure that well, only correct blocks are getting added. But whether that correct block is unique across the entire blockchain or not, you cannot ensure them immediately. We make a compromise there. Well, but eventually we solve this problem, this safety problem, that we will see later on, that after certain few number of consecutive blocks got added, we have an mechanism to select that well, if there are two correct blocks which have been added to a blockchain, then which one I am going to choose next or which one I am going to select next. We have a mechanism to do that, but immediately you cannot ensure this. Well, and then comes my liveness criteria. What liveness criteria says? That add a block as long as it is correct. Well, so do not keep on waiting for finding out that whether that block is a unique block that have been proposed by only this miner or not. Rather, what you do, that the moment you have valid transactions from the unconfirmed transaction list, you add them in a block, put the block in the blockchain well through the consensus mechanism and proceed further with the next block. Well, so it is not like that you keep on waiting for the ensuring safety for the correct block and then only you proceed to the next block. Well, the moment you have found out that the block is correct, just push it, forget about that, move for the next block, and the network has a mechanism that eventually it will choose one of the multiple blocks that got connected as the next block. Well, so here this way we ensure liveness. Well, so that means two or more different miners may add two or more different blocks in the blockchain at an instance of time. Well, and later on we will do that resolution, that which one we are going to consider. We do not need to do it immediately. So, that way what we do, that something called consensus finality, I will use that term later on as well, but just for your reference just remember this term consensus finality. The consensus finality is something that is ensured by our safety 1 criteria, which actually says that well, the block which you are going to add, it is the final block, it is a unique block that we not consider for the time being. So, that means the consensus finality is not ensured and we move forward with the next block. So, let us see that with this assumption that I am going to ensure safety 1 and liveness. So, these two we are going to consider and the safety 2 we are going to ignore for the moment. So, with that how we can design a consensus mechanism. So, what happens that the miners they pick up a set of transactions from this unconfirmed transaction list and prepare a block. Well, and every miner does this independently because the miners do not know each other. So, I do my own job well and the network will say that whether my job is successful or not. So, I do not bother about what other miners are doing. Now, you remember that whenever you are creating this new block as a miner, you do not have any fixed ordering of transactions, you do not have any fixed number of transactions in a block. Well, but what we have, that we have a limit on the block size, just to ensure that within a finite duration, typically in the Bitcoin blockchain it is something close to 10 minutes. That means within that 10-minute duration a block can be added in the blockchain. Well, just to ensure that there is a limit on the block size. So, in typical Bitcoin blockchain earlier it was 1 MB, nowadays it is 8 MB. So, there is a upper limit. So, your single block can be of size that much. Well, now how many number of transactions you can put on that block, you can do it. Well, so you do not have as such any upper bound or lower bound that this many number of transactions you need to put. Well, there is obviously a lower bound, you should have one transaction, at least one transactions to make a block, but there is no as such upper limit. And also there is no ordering of the transactions. Well, so I do not have any kind of ordering service which will prepare the transactions in some fixed order. Well, and that is the reason in the case of double spending, we have seen earlier that it might happen your second transactions get committed, but your first transaction is declined. Well, now once you have this set of blocks, once this set of blocks have been prepared, then what we do, we move back to that challenge response idea. Well, so the challenge response idea was that the network will throw a challenge and everyone individually will try to solve that challenge, and once you are able to solve that challenge, then you put a proof that you have solved the challenge. Well, and that proof will work as the guarantee that you have generated the block. Well, now in case of Bitcoin, Bitcoin blockchain, or rather proof of work blockchain, we combine multiple ideas together. One hand we need to have a formation of that blockchain, and at the same time I need to ensure this kind of consensus procedure. And the challenge that we are going to pose here, as I mentioned earlier as well, that generation of this proof should be complex, because the miner should spend some time to generate the proof, because my idea is that I want to give a complete random challenge such that different people take different times, so that the person who is been able to solve it first, ideally that person's blocks get added. Well, there is also no guarantee that if a person solves the challenge first, that block will get added. So, we will see later on, we only need a valid proof. But ideally what we believe that, well, once a person is able to solve the proof, that person is going to broadcast the block, and if other miners are able to see that newly generated block, then they basically forget about solving that problem further. Well, so that way my generation of the proof should be complex, but verification should be easy. That the moment you have generated the proof, others will be able to verify it in an easy way. And what we have seen earlier, that this cryptographic hash function plays a nice role in providing such kind of proof. So, you have a function something like this, y equal to hash of x plus some nonce n, and you have this y given, exactly not y is given, rather what we say that y should be less than some given target, say y t. Well, so that way you need to generate the y. X is given. So, x comes from, as we have seen earlier, the Merkle root of the transaction. Let me name it as MR, certain timestamps t, and the important part is hash of the previous block. Well, now here this particular hash function is serving two different purposes. Well, what is that? First of all, in this x I am putting up the hash value of the previous block. So, that way the hash that I am going to generate from the current block, it also contains a component of the previous block, and that way with this hash function this chain is getting connected. Well, so in the context of your blockchain data structure that Professor Shural has covered, you have seen that. Well, now the same hash function is serving the purpose of this open consensus. Now, to generate the hash function, the challenge that we are putting, that rather than directly computing the hash of x, what we are doing, that we are putting up certain value called nonce, and your x is known, your y has been given certain target, that y need to be less than some target value, say yt, and you need to find out these norms. Well, so you need to find out the norms. Now, when you need to find out these norms, this is a challenging problem that we have seen earlier. So, you do not have any kind of deterministic algorithm to find out the norms. Well, so the miners need to try themselves repeatedly to see that whether they can get a valid norms which can put up y less than equal to that target value of y. Well, so that way this is something interesting, and that you should keep in mind that this particular hash function, it is serving both the purpose. On one hand, it is helping to establish this link, well, the link between the current block and the previous block, well, because the hash function, the x contains an instance of the previous block hash, well, and at the same time the nonce value, the component of nonce which is there within the block, that is helping me to generate this proof for every individual miners. So, every miner, they have a block, well, the previous block hash they can get it from here. So, from the header of this block they can get yp, say yp is the previous block hash. So, they get yp, well, so they get the Markley root of this set of transactions, say this is m, well, they get the timestamp, this is something that constitute x for this miner, well, and now you find out y such that y is equal to hash of x append some nonce, and it has been given that y should be less than y should be less than some target value. Okay. So, that way every miner for the block that it is going to propose, it is going to find out this nonce value. So, the same thing will be repeated for miner 2 as well as for miner 3. Well, so everyone is going to find out the nonce for their block. Well, so that way you see that is again something interesting, that the nonce that is going to be found out by individual miners, that is different for different miner. So, miner 1 is going to find out some n1, miner 2 is going to find out some n2, miner 3 is going to find something as n3. So, their target is different. So, what is common across all the miners? So, this previous block hash yp, that is common. Okay. So, miner 1 is using yp, miner 2 is using yp, miner 3 is using yp. Well, and this target hash that I have, that means the yt, well, that is common for all. Well, because that depends on the current state of the blockchain, that how many blocks have been already been there in the blockchain. Depending on that, yt is generated, that we will see later on, that how yt is generated, but that yt is something which can be inferred from the current blockchain. So, yt is common for all the 3 miners. Well, so I am again writing. So, this target hash which is yt. So, yt is common for all the 3 miners. So, the previous block hash, say the previous block hash was yp. So, this yp is again common for all the 3 miners, but the Markley root are different because they have different blocks. So, for this miner it may be M1, for this miner it may be M2, and for this miner it may be M3. So, the Markley root is different, and at the same time the timestamp of generating this block, that is also different, because as we are working on a distributed system, it is not like that the hardware time is synchronized across all these 3 miners. Well, so I am writing it as T1, T2 and T3. Well, and from these values they are going to find out the nonce. Well, so the target nonce for miner 1 would be N1, the target nonce for miner 2 would be N2, and the target nonce for miner 3 would be N3. Now, they have different target. Now, if because they are trying randomly, or means it is just like a kind of brute force method through which they have to find out this target nonce. So, that way it is likely that every miner will take different time to find out the nonce. Well, so that way every miner is now trying to find out the corresponding nonce value, and my expectation is that one of these miners will be able to generate the proof. Well, because they have different target, everyone is trying a brute force method. So, eventually someone would be able to generate the proof. So, assume that one of the miner is able to generate the proof. Well, so miner 3 here, that particular miner is able to generate the proof, generate the nonce. Well, so I am naming it as NM3, nonce for miner 3, that is the proof. Now, once this miner is able to generate the proof, what that miner does, that miner sign this particular block and broadcast it over the peer-to-peer network. And earlier I have mentioned that we use a protocol something called gossip. So, that is basically gossip over the network, and once certain node is getting that block, they will be validating that block, and after doing the validation, they will be adding that block to the existing blockchain, and eventually the other miners will also be able to see that one of my fellow has been able to generate a new block. Well, and that block contains the proof, and by virtue that generating that nonce is difficult, but verification of the nonce is easy, because for the verification you have all the information in hand, you have the Merkle root, you have the timestamp, you have NM3, and at the same time you have the previous block hash. So, you can just use that value to compute the current block hash and check whether that current block hash is equal to the block hash for miner 3 or not. Well, now once you have that information, you can do the validation, and once you have done that validation, you can simply forget that, well, I am a failure, I have failed for this instance. So, let me try for the next instance. Well, another thing this miner does, that whenever they see that, well, a block has been generated and the transactions correspond to that block has been added. So, what they do, that they remove this committed transaction from the unconfirmed transaction list. So, the transactions which are there in this committed block, they remove those transactions from their unconfirmed transaction list. Well, so after they delete it, then they start the next round, and remember that again we are in a asynchronous system and in an open environment. So, it can always happen in the next round a fourth miner 4 has joined the system. Well, so that miner is also again trying to generate the new block. So, that means in every round there is no fixed number of miners. In some round there might be a single miner who is trying to do it. For some round there might be thousands of miners who are trying simultaneously, and that way the system propagates. Well, so this is the kind of basic idea behind this proof of work consensus mechanism, but till now this entire consensus mechanism is not complete, because we have certain challenges that we need to handle. So, what are these challenges? That we are going to see in the next lecture. So, in today's lecture, what we have seen, that this Nakamoto consensus, it ensures that any correct block can be added, and there is no guarantee that every miner will try to mine the same block. Well, it is ideally that different miners will try to mine different block, and there is no guarantee that you can see your latest transactions in the block. So, it might always happen that the miners who have mined the block, they have not heard your transaction. So, that is why your transaction is not yet there in the block. Well, but the open question that is still there is that what if two miners mine blocks simultaneously. So, what we assumed, that eventually one of those miners will be able to generate the proof, but it is always possible that more than one miner has been able to generate the proof almost simultaneously, that within some minimum difference. Well, so we are going to see in the next lecture that what is going to happen in that case. Well, so this is all about today's lecture. Hope to see you all in the next lecture. Thank you for attending.